Hey folks, welcome back again. Wednesday morning here, or afternoon or evening, whatever time notes. Um, what we're going to do today is we're going to talk about Doppler effect. Okay, we're also going to talk a little bit about cleanup on some of yesterday's math problems. Saw a few things that I want to talk through and just make sure that we get all fixed up and everything like that. All right, so here we go. Okay. Just some guidance um, on some of these problems for us. Okay. Yesterday I showed you kind of quickly, and I apologize for that, the speed, frequency, and wavelength formula. But I didn't actually run any of those problems. Okay. So I apologize, and let me fix that up for you. Okay. So what you're going to see here is we've got the speed of sound is calculated to be 349 meters per second, right? Obviously through air. If a sound wave has a frequency of 500 hertz, find the length of the sound. Okay. So speed of sound, that's v, that's our velocity. So that goes in on the left side there. The frequency of the wave that we're using here is 500 hertz. Remember, that just is oscillations per second, beats per second, or I'm sorry, waves moving past it. Okay, that could be the compressions moving past it. That could be the crest moving past it. Okay. So in this case, now we want to find the wavelength of it. So the way we're going to do that is we're going to take 349 divided by 500. All right. Our lambda here, or wavelength, is going to be 0.698 meters. All right. Again, having that meters per second on the left side, isolate the wavelength from the lambda there, we have to divide over the 500 hertz. Okay? The other problem we saw yesterday, the difference became the length of the wave. The length of the wave was half a meter long. All right. So we plug that in similar to what we did on the other side. The only difference is now we're solving for frequency. All right. So we've got our wavelength being half a meter, got our velocity being 349 meters per second. Okay? So when we divide all this together, we find out that our frequency is 600 hertz. So kind of the way that we should run through it. The vast majority of you did a phenomenal job. And I know that this is probably repetition that you may not need, but there's a few out there who do need this stuff. Okay. So sound waves and the Doppler effect now. Doppler effect is something that's actually very, very interesting. It's something that you've experienced since really you became cognizant of being able to hear stuff. Okay. So the changing frequency results in the changing pitch. When we look at this concept of Doppler effect, the one thing I want you to understand is that the wave speed isn't going to change. So when we're looking at the examples that we use later on, understand that the wave speed that we have there, the speed of sound, will still stay the same, right? I have a YouTube video later that I'll talk a little bit more about on here as well. You're going to see the speed of light there as well, and that also will not change too appreciably through space and stuff like that. Okay, so for us, this is something familiar to us. We've seen the Doppler effect. You may not have actually heard the name the Doppler effect, or you may not have put the physics concept with what that sound is, but it's if there's a siren, a passing car, or a racing car. It's that sound when all of a sudden you hear that siren approaching and how the sound gets higher and higher and higher, and then it maxes out kind of at its highest point as it gets right next to you. And then as it goes away, what you start to notice is that sound starts to get lower, 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 lower. All right. It's in a NASCAR event or an F1 or an Indy car or anything like that where you hear that engine revving and that rev seems to get higher and higher and higher, goes by you, lower and lower and lower and lower. Okay? Same thing with that passing car. It seems to be the highest it can sound, the highest pitch it can sound as it gets closer. When we hear the Doppler effect, usually we're not moving. What that means is that we're standing on a sidewalk, and all of a sudden that ambulance goes by, or we're sitting in our seat at a racing event or something like that. Okay, or we're just sitting on the back deck of patio, right? And all of a sudden that thing comes by. Now, if that siren were to stop, it would sound the same the entire time. And if it were not moving, it would sound the same, right? If you sat next to a car as it was running, it would sound the same. Unless obviously if you have a Tesla or an electric car, that's pretty quiet there, right? Well, I suppose if you got the ones that shut off when you stop, that always weirded me out when I had those two. Yeah. Anyway, sorry. But if you got a normal, like high performance car, like most of you do, the high end sports cars, and you're sitting there and that engine is idling, it's going to sound the same, right? If you were to rev it up to X number of RPMs, revolutions per minute, it sounds the same yet as it sat there. But if that person then drove by you, right, you would hear that pitch start to increase, is what we call it. Okay. So we asked the question. Sorry, head and itch. How does this thing work? Now, I'm wondering if you know what this is. Some of you might. Yep, you're right. That's a tornado siren. All right. If you go up to King Park or All Saints, you may even have one in your neighborhood area there. All right. This is one of the ones like we have here in Lakeville. What happens is that this emits a tone, just a sound. All right. And there's a mechanism in there that causes it to rotate. Now, if you've been lucky enough to be outside, or if you've been, like me as a kid inside, and you hear this for the first time, we're classically conditioned to think, what? Something bad's happening, right? I vividly remember the first time I was home. I was about 12 or 13 at the time, and I heard the tornado siren going off. My little brother was with my mom or my dad, and so it was just me and the dog. And so what did I do? I got scared. I went down into our basement where we were supposed to go. We had a little spot underneath the stairs, so I took the dog, got her inside of there, and we just hung out there. And all of a sudden, the tornado stopped, or the sound stopped. And when I was outside, I'm like, God, that's so weird. Like, it's sunny out, and there's not a cloud in the sky. How is there a tornado? I came to figure out that they tested tornado sirens every so often. I know, crazy, right? But this tornado siren, it's going to emit a sound. As it rotates, what's going to happen is that frequency that you hear it at is going to change, right? As it gets more towards you, pointing towards you, that frequency is going to get higher. It will sound louder. And that's because that wavelength is going to get shorter. As it turns away from you, it will start to go down in pitch. It'll start to sound lower. Again, the frequency will start to decrease. The wavelength will start to get longer in between those successive waves. It's not that this is making a different sound as it's near you. It's the same pulse. It's the same rate. Okay? Now, there are other types of models out there that have, 4 or 6 or 8, cones in and around it. Okay? Those work by just rotating around through there so that they can still shoot the sound out as well. Yeah, so there's still a rotation. We just see the rotation. If you ever see one of these going off when it's testing, hopefully, then it's actually pretty interesting. I know it may not be, but okay. YouTube video for you. If you want to check it out, go see it. Not a bad one. It talks about light at the end. It's a little heavy. What I mean by that is that if you remember back when we talked about planets and the relative size of the universe, we started talking about redshift and blue shift in there in this video. It's kind of cool. I know you're looking at me like, it's physics, it's crazy, it's science. I don't know. I know, but it is still pretty good. Okay? All right. So if we look at kind of the Doppler effect from just this standpoint, all right, what we're going to see is if this source here is stationary, right, if it's not moving, all three people should hear the exact same sound. They should hear the exact same pitch. Okay? Now, the question becomes, what happens to frequency when our wavelength is increased? So if our frequency changes with wavelength, if the wavelength is increased, in order to keep this wave going at the exact same speed, because it's still just going through air and the speed of sound for it is not changing, then what that means is that if our wavelength is going to go up, then our frequency has to go down. So what will end up happening is that you will see is that as this thing moves, the animation is a little wonky. It doesn't go faster than that. That would be, I suppose, breaking the speed of sound, so right? Mach 1. What happens is the person on the right should hear a stacking effect. The pitch should go up, right? The person on the left, because those waves are getting further apart, should hear a lower pitch, a lower frequency, right? The person in the green, what they should have is they should have it start, relatively low, and as it gets closer to it, high. As it goes by, low again. Okay, so it should change. All right. So again, person in the red is going to hear high frequency, right? Low wavelength. Wave speed, still the same. That's a beautiful thing about all three of these people. The wave speed for each and every one of them is still going to be the exact same. All right. It's just that the frequency in the red is going to be high. Pitch is high. Sounds high. In the blue, low. The frequency will be low. The wavelength, longer. All right. The pitch will sound lower. In the green, it'll change. It'll go up and then back down. Okay. Now, we can actually start to calculate this as well. I know you think this is awesome, right? So, write this one down. F prime on the left side there. That's the shifted frequency. That's what we're hearing. All right. If we're the observer, okay. The original frequency, that's the one that the source is releasing or allowing to go out. Okay. V itself, V is the speed of sound in the air, okay, or the speed of sound in whatever medium. No, I don't mean to say that it always has to be the air. We can use this with submarines and stuff like that too. Okay. The velocity of the observer, pretty self-explanatory. Velocity of the source, pretty self-explanatory. All right. The units measured for this, the frequencies, the top two Fs are going to be hertz. The Vs are going to be meters per second. Now, folks, this one can be nasty enough as it is. I'm going to mess with you on this one. You'll get meters per second. You'll get hertz. All right. So, if we have a moving observer, stationary source. All right. So what this means is you're pedaling your bike, and all of a sudden you see an ambulance or a fire truck, and it's stopped. And so what are you going to do? You're going to ride your bike towards it just to see what's going on. All right. As you pedal towards it, if that is just playing a stationary tone, then as you get closer, we can figure out how fast you're actually going. Okay. All right. Moving source, stationary observer. Oh man, this brings back an interesting memory. My first ever concussion was when I was about probably 4 or 5. Right. The house I grew up, or one of the houses I grew up on, was on the main drag. I remember very vividly because lots of traffic out in the front, so my mom always told me to be careful out on the sidewalk. Right. So I was sitting in the neighbor's driveway riding my big wheels. Don't know if any of you know what a big wheel is. Big front tire, small little back tires. Think of a tricycle, but the front wheel is excessively large, right? Ambulance drives by. Perfect Doppler shift or Doppler effect, right? I'm excited because I think ambulances are cool. And the people who drive them, even cooler. So what do? Lift up, show them my big wheel riding a wheelie. What happens? I don't understand physics because I'm 4 or 5 years old. I pull the wheelie too far. I end up rotating around the back 2 wheels and end up hitting my head on the concrete. That was the first thing that landed. The rest of the day is somewhat of a blur. My mom tells me she took me to the doctor's office. I wanted mac and cheese and a nap, shockingly, as a 4-year-old, right? But it was interesting because there in that moment, I was the stationary observer and the ambulance was coming nearby me or coming across from me. So what I could have figured out was, I could have figured out how fast that ambulance was traveling if I knew the frequencies of those. Not going to happen, right? Okay. So here again, here's your base formula. Now, you don't need to know the individual iterations of this, whether it's the observer's not moving or the source isn't moving. This one is perfect for us because remember, if our observer's not moving, that's zero. So VO is zero. If the source isn't moving, guess what? VS is zero. Well, what if they're both not moving? Does the frequency change? No, it doesn't. How crazy is that, right? Which should make practical sense for us. All right, let's try one out. All right, so here we go. So Linda's out for a run. She runs towards a parked car that is blowing its horn because her friend Linda with a Y, is trying to get Linda with an I's attention. Linda with an I knows that the natural frequency of the car horn is 400 hertz. Who doesn't know that? I didn't. But as she's running, she hears the same horn at 407 hertz. Linda with an I has a very, very sensitive and tuned ability to understand the different frequencies. Okay. How fast is Linda running with an I? Assuming the V of sound is 345 meters per second. Okay. So we want the observer's speed. So we want Linda with an I's speed, right? The source, how fast is it moving? That would be the parked car. It's not moving at all, though. Okay? So it's moving at 0 meters per second. Speed of sound, 345 meters per second. All right? Our frequencies, the original frequency that the car horn had was 400 hertz. The perceived one that Linda had was 407 hertz. All right? So we plug everything in. Now, let me show you the steps on how to do this thing. So the 407, that's the one that Linda heard. The 400 is the one that was from the source. That was the original. 345, how fast everything's moving, or how fast that sound is moving in the air. All right. Our source on the bottom, 0. Right. Again, the reason for that being 0 is it's not moving. All right. Directionality does become important. All right. Our observer, that's the one we're going to find out. Okay. All right. Let's start running this thing. So I cut out the source on the bottom there. All right. First things first. Now the physics is done. This is where algebra can become our greatest weakness, right? So if I want to isolate VO, right, what I'm going to do is I'm going to divide by 400 first. Okay. So now on the right side, I've got 345 plus VO divided by 345 equals 407 divided by 400. Now you can cross multiply, divide, do all that sort of stuff, right? I'm going to multiply both sides by 345 to get that right side so it's all by itself. All right, there we go. So 407 over 400 times 345, that equals 345 plus our velocity of our observer. Now, if we forget to do this next step, then a crazy thing's going to happen to Linda who's running towards it. She's going to be running faster than the speed of sound. I don't know about you, but it's always been a dream to be able to run faster than the speed of sound. Unfortunately, the reality is it's not going to happen. I can't do it. I can barely crack, double digits in the miles per hour world. Okay. All right. So anyway, we have to subtract over that 345. Okay. Once we do that, what we're going to find is the 407 times the 400, or divided by the 400, and the 345 gives us about 3. Okay. So 350 meters per second, that's moving pretty fast. If you want to figure out how fast that is, multiply it. Okay. So what we see is that Linda is running at 6.04 meters per second. So she's going about 13 or 14 miles per hour. She's excited to see her friend. Just like I think all of us would be if we're given the opportunity right now to see our friend, right? Okay. All right. So, thoughts. If you have questions or stuff doesn't make sense, give me a shout, right? Send me an email, hit me with a direct message through Twitter, anything like that, all right? Tomorrow after school from 2:45 to 3:15, I'll have office hours just because tomorrow's Thursday, Friday, we got that. Don't forget about that part. All right. On the right side here, just another image for you looking at Doppler effect. If you can find interesting YouTubes of them, of Doppler effect, I'd love to see them. I know there's some cool stuff out there that I barely scratched the surface on. So, all right. Otherwise, that's what I got for the day. Homework 16.2 is available through email and through Schoology. Hope you have a great day, and we'll talk to you later, okay? Take care of yourselves, folks, all right? See ya.